And hopefully that starts at the beginning. Nope. Function. Yep. Welcome to our Friday class.
I'm just gonna find.
We are going to go through chapter 2 stuff today. I don't think we'll start chapter 3, but we will finish chapter 2. So you can see here the things we've talked about. We've talked about forces, what the normal force is, what frictional force is, what the force of gravity is. And we've talked about what equilibrium means. And we learned two different things. If we have constant motion, then the system's in equilibrium. And equilibrium means equal forces, or the sum of the forces is 0. And then we've defined acceleration. I'm going to pick up talking about kinematic equations and then go through Newton's laws. So we had this clicker. So I'm not asking you to answer the question now. If a falling object gains 10 meters per second each second, what do we call this 10 meters per second each second? What's the name for that?
Oh, 10 meters per second.
Yeah, what's the name for that quantity?
What?
There's a special name for it. What is a meter per second a unit for?
Time. Oh, no. A distance.
Okay, distance is meters, seconds is time. So what is meters per second? Distance per time. Yeah, velocity or speed. The difference in speed and velocity is if it has direction, it's velocity. If it doesn't have direction, it's speed, but they both have units of meters per second. So this is speed per time. So it's a rate at which the speed is changing, and we call that an acceleration, which was on the line below, I noticed now. And so this here is the acceleration. We often use a special thing, g, if it's the acceleration due to gravity. And I can't help myself. I will always write 9.8 meters per second squared. But like I said, the textbook uses 10, just rounding it, and you're free to do that. So with that, if I have a ball dropping, its speed is changing by a fixed amount each second. How much is the speed changing per second according to that acceleration? Each second the speed changes by 9.8 meters per second. Now, the textbook, like I said, uses 10, and so that's why it has the speed goes 0. After 1 second, it's 10 meters per second. After 2 seconds, 20 meters per second, 30, 40. It's just increasing by that acceleration amount each second. Now, the distance, that's more complicated, isn't it? That's not a simple going up by the same amount. But that makes sense because remember, the distance that something travels is the speed multiplied by the time it travels at that speed. So if the speed is faster later on, the distance it covers in a second also has to be bigger. And so we use calculus to derive an equation to tell us what the distance will be as a function of time. And of course, this clearly not being a calculus class, I just show you the equations. So here's the equation for speed. The speed at any time, so v is our symbol for speed, is equal to the initial speed, v subscript 0. The 0 just means at time 0, plus the acceleration multiplied by time.
And you said because we don't have to memorize these, you'll just give.
You do not have to memorize them. They will be on a sheet you're given with your test. And then the second one, so the first one, that's kind of logical. It's the same equation as we've seen all along, just solve for a different thing. Before we saw change in speed as acceleration multiplied by time. And now we're just writing, well, if change in speed is acceleration by time, v minus v0 would be change in speed. Add the v0 to the other side. It's the same equation. This is the same as that equation. It's just resolved. But the second one's a new one. The speed, the position that an object has is going to be the initial speed it has multiplied by how much time has passed plus 1/2 the acceleration multiplied by time squared. So let's test this. You had to, for your homework, you actually had to do this, and I felt really bad that I didn't have it covered before you turned it in. No one asked in class, or I would have gladly worked through it then. You had to verify that after 3 seconds it was 45 meters. So that was one of the homework problems.
Oh, right.
So how we would do that is we would say, okay, the distance at 3 seconds, so I'll put a subscript 3 seconds, is equal to the initial speed. Well, what was the speed when it started? It tells us it started at 0. 0 multiplied by 3 seconds plus 1/2 the acceleration. They use 10 here, so I'm going to use 10 to match the textbook. 10 meters per second squared, then multiplied by the time, 3 seconds squared. So I just plugged in the values for time and, of course, the value for acceleration and the value for the initial speed. And then if you calculate that out, 1/2 times 10 is 5. 3 squared. Remember, what does it mean? This may be demeaning to you, and I don't need to be demeaning. But some people are stronger in math than others. So what does it mean if I have my 3 seconds and then I have superscript of 2?
Squared.
It means squared, but what does squared mean?
Means to that, yeah.
Multiply by itself. Okay, I just want to make sure that that's clear so we don't have somebody like, I'm not quite sure what he's writing up there.
Can I use my phone and take a picture of that?
I'm sure. Or remember, it'll be uploaded on Moodle afterward. So you can look there as well. I say sure like it's the most obvious thing, but I have other colleagues who have said, I have students who want to take pictures, but that's my stuff. They can't. Okay. I think that I want to share my stuff with the students so they can learn. But back to the point. So 1/2 times 10 is 5, and then 3 squared, 3 times 3 is 9, 5 times 9 is 45. So this is equal to 0 plus 45. Now let's look at the units. Units are an important thing. You might remember from the first or second lecture, I talked about how units are important. You know, it could be 45 miles, it could be 45 meters, it could be 45 millimeters. You need to pay attention to your units. So if you look at the units, I had, for my acceleration, meters divided by seconds squared. And then I had 3 seconds quantity squared. What that means is I have 3 seconds times 3 seconds, so I have seconds squared in that unit. And so the seconds squared here cancel with the seconds squared there. And I'm left with meters. Everybody understand how we did this?
Oh yeah, it's still clear.
It's good that you're not being sarcastic because here's a problem for you. Here's a problem for you to do. And it's slightly more complicated. Just like with tests, we have these simple little questions that we do in class, and then on a test you have something with a little twist on it just so it's not the same.
Is this lecture free? Kinetics and dynamics.
Is it what?
Never mind.
Is it
Don't
free?
worry about it. No, don't worry about it.
Okay.
Never mind. It's free.
So a ball is thrown upwards with an initial speed of 5 meters per second. What are its speed and position 2 seconds later? Hint, use up as positive. So the initial speed is a positive 10 meters per second, and the acceleration is a negative 9.8 meters per second squared because it's down. And of course, you're free to use 10. So, I mean, what we're doing is exactly this problem. Throw it up, comes down, and after 2 seconds, what's its speed and position? So I want you to and work with the people next to you. So for instance, Alex, you come up work with these two. Because 2 grams are better than 1.
Question.
Yes, ma'am.
Which lecture are we on?
5.
Right.
So wouldn't the extension of the rule? I'm going to ask because I'm not quite sure and I'm not that math.
That's fine.
5.
Well, an upward and initial speed for the speed of collision of 2.3. So A is the acceleration.
Right. That's what I thought. Is that right? That's what I'm talking about. Right, so I wanted to tell you, I literally, like,
Is it supposed to be this one?
It's all correct except for.
all I want is to have
And excuse me, incorrect.
Wait, why is there a goes negative G minus negative 9?
Well, if you use up as positive, the acceleration of gravity is down. And so that's why it's a minus. And G is 9.8 meters per second squared, so
I don't know,
minus G is
because
minus.
I'm not good at equations, so I'm very confused on how I'm supposed to process.
Yeah.
No, G is given to you. But acceleration is part of the problem, right? The equation has acceleration.
Yeah.
So G is the negative 9.8.
No, G is positive 9.8. Minus G is negative 9.8.
I want to.
G is always a positive value, and then we assign the sign based on the direction.
So
the
it wouldn't look
acceleration
like
is
that.
minus.
I'm very
Okay, that's the equation for speed. Is that right?
It's the equation,
The
if I
first one?
put in the, yeah.
Okay, so it should be 5 meters per second plus 2 seconds times minus 9.8. That's actually not equal to 5. So this part here is right, but what you put in your calculator didn't come out right.
Oh, I don't need that part then. I didn't put in
No,
my
you're solving
calculator.
for that. That's what you're finding.
Oh, okay. So I'm not even putting anything over here. That's what I'm
That's what
looking
you're
for.
finding. That's
Okay.
correct.
Oh, okay, that makes sense then.
So what do you have to find? This is not
What do you have to find D?
at all.
Okay, also find the feet.
Talk to me, what's happening?
We're just doing the equation. So you're gonna enter in what is the equation there. So for the first one, for velocity, you're gonna enter in the numbers in the word column to the problem at the bottom, the first column, and then you're gonna find it on your calculator. So would it be like plus 2.0 times negative 9.8?
Except for the order of operation. It
Yeah.
did it as a subtraction problem instead of.
Okay. So I would wanna do this first, and then I have that, right?
Yeah, definitely do this first. That's correct.
Okay.
What did you do?
She did them right.
Yeah.
Okay, so then the other one is gonna be exactly like this, except we're putting in.
You see what you did, so. Okay, so you started right. It's 5 meters per second, and then you have plus, and then you should have minus 9.8, because the acceleration is minus 9.8. Oh, okay. And then multiply it by 2, because the time is 2 seconds. So 9.8 times 2 is 19.6. I've done that calculation a lot of times, trust me. So you have 5 minus 19.6.
Minus
Well, remember that was a minus sign.
Yeah.
But we also have 5, so it's 5 minus 19.6. The 19.6 is second. Yeah, there we go. And so 19 minus 5 is 14, so it's minus 14.6. What did you miss?
Should be there.
Okay, and then we have the acceleration. I know we got a couple people texting over here, so they're clearly done. I think everyone's done at least half of it. So I will do the calculations here so we can see. Now in physics, we always draw pictures. Amy had me take are you a visual learner thing? And it came out, according to her thing, that I am. I don't know about that, but I know that the visual process is important in physics we have a ball that goes up, but the acceleration is downward. If the acceleration is downward, that means the speed is changing in the downward direction. So it started going up, but it's going to change downward, which means it's going to slow down, come to a stop, and then come back down. And so I want to find, after 2 seconds, what its speed is and what its position is. So then using the numbers we have, my speed is equal to my initial speed. So there's the initial speed, plus the acceleration, which is minus 9.8 meters per second squared. If that second doesn't come, or meter doesn't come back, I'll put it back in. Multiplied by the time. So there I have just replaced the variables in the equation with numbers. In physics, we do a lot of math. It's symbols standing for numbers. And then I'm solving for that unknown, the speed. And so as I was working through with other people, 2 times 9.8 is 19.6. Got to keep the minus sign because of this minus sign here. Looking at the units, 1 second cancels, so I'm left with meters per second there. This was still 5.0 meters per second. So 5 minus 19 is minus 14.6 meters per second. So there's my speed at 2 seconds. And then we wanted to do the acceleration the distance as well. So using the distance equation, what's my initial speed? Right there, 5 meters per second. Now this is multiplied by the time of 2 seconds, plus 1/2 my acceleration, which was minus 9.8 meters per second squared, multiplied by my time of 2 seconds squared. So if I do my math now, 5 times 2 is 10, right? 10, and meters per second times seconds, the seconds cancel. That's just 10 meters. I have this minus sign is going to make it a negative here. I'm erasing that circle so it doesn't confuse. And then I have to do my math. And I like to do math in my head as much as I can. I have 1/2 times 2 squared, which is 1/2 times 2 times 2. 1/2 times 2 is just 1. So in the end, that's just a 2 times 9.8. I told Alex, I've done this a lot of times. 2 times 9.8 is 19.6. And looking at our units now, since this is a square here, this is second squared divided by second squared, cancel meters. And so that's minus 9.6 meters. So there's our 2 answers. We're able to find the position of the ball 2 seconds after it was thrown up. Now, a couple more questions before we move on. The first question is, after we've done it, does that make sense how we can calculate these things? No?
I mean, yes, but I'm still going to struggle when it comes to the test.
Well, you can come talk to me and I can help you work through more things. But because my goal is for you to be successful. The basic process was we have to identify what our variables are. So that's why I had this hint here to help us get our variables set up. Using up is the positive direction. So things that are downward, the acceleration was downward. So we use a minus number for that. Then we just put the numbers into the equation. We had to identify the correct equation, the correct numbers, and we put them in. What does it mean that V equals minus 14.6 meters per second?
Velocity.
Okay. Velocity has a magnitude of 14.6 meters per second. What does the minus sign mean?
It's falling down.
That's going downward, not upward. What about the D is minus 9.6 meters? What does that mean?
The speed of it is going downward? No, the time.
D.
Distance.
The distance. it's 9.6 meters. Because it's a minus sign, that means down or below where it started. I said a couple more things. Yeah, still at least one more thing. Who's been messing with this? When I threw the ball, while it was in my hand, was its velocity changing? When I was throwing it. Annabelle says yes, and she's correct. While I was throwing it, it was changing speed, so it had acceleration. What direction is the acceleration if it started at rest and it ended up going upward? Because the change in velocity was upward, it was a positive acceleration while it was in my hand. But once it left my hand, then it was in what we call free fall. And don't put that down for your potential test question because that's not the topic du jour.
No.
But it was in free fall, which means it was falling only under the influence of gravity. So under the influence of gravity means it has an acceleration that's downward of 9.8 meters per second squared. So as it was going up, what direction was the acceleration?
Positive.
After it left my hand, as it was going up,
It was considered free fall.
it is free fall, which means the acceleration is downward, which made it slow down. Now, when it was coming back down, what direction was its velocity? That actually is a redundant question if you think about it.
It would be back down.
Right, when it's coming down, the direction it's moving is down. What about the acceleration? What direction was the acceleration when it was coming down?
Negative.
It was down, negative. Since the direction of the acceleration was the same direction as the velocity, it was getting faster. When it was going up, the direction of the velocity was opposite the direction of the acceleration. It was slowing down. What about at the top? What was the speed at the instant it was at the top of its flight?
The slowest it could be
Which is 0, right. So the speed was 0 up there. What about the acceleration? This is the payoff point. This is the part that most people get wrong unless they really think it through.
It would have been 0 as well. No.
It can't be 0. That's what most people say off the bat because they have in their heads a confusion between velocity and acceleration. The acceleration is the rate at which velocity is changing. The instant before it was at rest, what direction was it traveling? Up. The instant after it's at rest, what direction will it be traveling? Down. So the change is the final minus initial. So it changed in a downward direction, so its acceleration had to be down. So even at the top when it's momentarily stationary, the acceleration is down. And there's a really easy way to make sure that you don't make that mistake when it comes to test time. If the velocity was 0 and the acceleration was 0, then what's happening to the velocity? Acceleration is 0, what's happening to the velocity?
It's holding still.
It's staying constant. And so if the velocity is 0 and it's staying at constant velocity, what's the ball doing? It's just hovering. But we know when I throw the ball up, it doesn't hover at the top. So it cannot have 0 acceleration at the top. Okay, time to move forward to another topic. As soon as I find where I placed my pen as I was walking around. So, in lab yesterday, what was the point of the lab yesterday?
To experience Newton's second law of motion.
Okay, to experience Newton's second law of motion, to verify how force affects motion. That when you have a force, it makes things move. So you had two things at the end you had to answer that related to the motion and the force. You had one that was, if you double the force, keep the mass constant, what happens to the acceleration? What did you answer? Hopefully you all answered right. If you doubled the force but kept the mass the same, that is, when you went from 4 washers to 8 washers, what happened to the acceleration? It went up. So the acceleration was directly proportional to the force. Then when you kept the same force and you increased the mass, it was indirectly proportional, the acceleration went down. And so those outcomes were the testing, the predictions of Newton's second law. Remember the scientific method. You notice something interesting. I push something and it moves. And then you come up with an explanation. And Newton said that that force is causing acceleration, blah, blah, blah. And he came up with the equation, net force equals mass times acceleration. And so Newton's second law has the equation. There's two ways of writing it. They're exactly the same. Our textbook prefers the second one. Acceleration is net force divided by mass. So I have an object. Let's say that object is this ball I've been throwing around. Oh, didn't put it back in here. Okay, let's say it's this ball then. Yeah, there it is. So here's this ball. If I put a force on it, it will accelerate proportional to that force. Now there's a really simple thing we have to keep in mind. If I set this ball on the tabletop, is there a normal force acting on the ball right now?
Yeah.
Yeah. What direction is that normal force? Keeping it from falling through the table.
So there's one going up and one going down.
Right. The normal force is coming up out of the table, and you jumped a step ahead of it. The normal force is upward, but it wasn't accelerating upward. That tells you right away that equation cannot be correctly written as F equals ma. Even our textbook writes F equals ma. It drives me crazy because that's just not correct. It has to be the net force. The net force is when you add them all up. So if we go to what Alex said, there is an upward force, the normal force, and a downward force, the gravitational force. And since the acceleration was 0, we knew that the net force had to be 0. Now if I take this and I throw it, the net force is not 0. And so then it accelerates as per Newton's second law. So the net force acting on a single object divided by the mass of that same object is its acceleration. That's Newton's second law. So here you see it written out in math form. What does this little arrow mean? Direction. So Newton's second law is a vector law. It has direction involved. So if you have a force acting on something, it will accelerate in the direction of the net force. I've been saying net force and putting a subscript net. What does net mean? Your net income. What is that?
Max. Well, no, the average. Like
Average.
It's not really the average. That would be mean. But the net is if you add everything together. So my net income is going to be everything I gain minus everything I lose. And we hope that number is not negative. We also have this Greek capital S, sigma. And we use that symbol to mean sum. So that just means add them all up. So net force and sigma F both mean sum of all the forces. So those two forms are exactly equivalent, and you'll see it both ways. So you have to have a little comfort in seeing that. And in words, well, there you have acceleration is net force divided by mass. And so we have simple examples we could use. Let us say that Annabelle punches her Glacier View Ranch water bottle as hard as she can. What's the response of that water bottle going to be?
It's
It's going to go flying. It's going to have a pretty big acceleration. Now let's say that instead of punching her water bottle, she punches me. What's the response going to be? We're not demonstrating, no. I know this is a demonstration of sorts, but it's not a physical altercation.
I really learned your demonstration. Same.
Okay, choose something.
Well, I thought we were doing it with the
So if she punched me, not taking into account any reflex I might have, how am I going to respond?
You're gonna say ow.
I'm going to say ow.
like your body, like you'll probably go back.
I'll probably go back a little. But I won't go flying like that would.
Yeah.
Because what's the property we've learned to call this?
Mass is greater mass.
So that's
Inertia.
inertia, right?
Oh,
Because I have
yes.
more inertia.
I know.
You're working together, teamwork.
Whatever. 75, 25.
So we have here now a quantification of how that inertia works. That the acceleration is the net force divided by the mass. You know, when your phones are down in your lap, it's still pretty obvious that you're on your phones.
Oh, I wasn't trying to be like that. I wasn't trying to be sneaky.
Okay. So Newton's second law. Now, we've talked about acceleration of gravity, and now we're just going to look at how Newton's second law and the force of gravity we've learned tells us the acceleration of gravity. So we learned that the weight of an object is equal to mg.
MG.
And so if I have a ball that's in free fall meaning nothing else is acting on it, then the only force acting on it is force of gravity equals mg. And if I apply Newton's second law, the sum of the forces divided by the mass should be equal to the acceleration.
Wait. Never mind.
So sum of the forces, the only force in my picture is mg. So that's going to be mg divided by m. And voila, those m's cancel. And we have the acceleration is g when it's in free fall. It's a very simple calculation to show why in free fall the acceleration is g, assuming that we are accepting that the force of gravity is mg. Newton, during the Black Plague time when he didn't have to work, he did nothing but physics. He invented calculus, he invented these laws of physics, and he invented the universal law of gravity. And that equation, force of gravity equals mg, comes from his universal law of gravitation, and from that we find the acceleration of gravity.
So we know for a fact that an object in free fall is always 10 meters per second, no matter what it is.
In free fall on near the surface of the Earth. We have to specify that, because like if you're on the moon, free fall would be different.
Oh, that's a good question. If you don't have a question.
She's just trying to get you to
Alright,
all
Duffy.
put it down. You cannot have somebody else do your question for
It's
you.
not, I just don't remember it, and she knows verbatim. I already put my name.
Verbatim.
Why don't you just tell her and she writes it?
Okay.
Why don't we continue with the lecture? Now, here's a question.
An object in free fall is accelerating at what rate? Well, an object close to the Earth is accelerating at what rate?
Here we have an example of one brick versus two bricks tied together. You drop one brick and you drop two bricks tied together. How is the acceleration going to compare between the two?
It's going to be the same because we just learned
That's
that
right.
if it's close to the Earth, it's 10 meters per second.
Regardless of the
Yes.
mass. So let's go back to Galileo Galilei. Maybe he did dropping two different masses from the Leaning Tower of Pisa. The point was an experiment that could potentially disprove a hypothesis that the speed at which they fall is proportional to how much mass they have. That was Aristotle's idea. And Galileo's idea was, no, it's independent. And so we saw a demonstration of this that was reasonably dramatic. We saw, well, it was a hammer versus a feather. You guys remember the video of the hammer versus feather?
Yes.
Where was it done?
In
Space.
On the moon.
Okay, but that's my next question. I feel like a feather always is slower.
If there's air, the feather is always slower. But on the moon, there's no atmosphere. So when he dropped the hammer and feather on the moon, there was no atmosphere. And when I was a kid, obviously I grew up in Earth. And so when we were
There
driving
was no
from
question.
the Monterey Bay Academy to Santa Cruz, I would have my hand out the window and I'd be going, feeling the wind blow my hand.
That's a nerd thing to do. Apparently I'm a nerd too then.
Excellent. So I felt a clear air resistance on my hand. I felt the air pushing my hand backwards.
You kind of go with it. And it's
Yes, I gave waves and yeah.
I did that too. Like I was
Good.
walking away. Wow, you're a loser.
No. So that air resistance affects us. And at least with me, right, I would go like this and feel a lot of air resistance, and go like this and feel very little air resistance. Well, we have that idea here with the feather. The feather has a fairly big area, but its weight is fairly small. So its air resistance is fairly big, but its weight is fairly small. Hence, the air resistance really slows it down. Whereas the rock, even though it's bigger, its mass is way, way bigger, so the force of gravity is much bigger, and it's not as affected by air resistance. What were you saying, Jessica?
Well, so then it's no longer 10 meters per second when it applies to a feather, but that it can't just be enough. See, now I'm like,
Well,
now my
because
whole thing is ruined.
technically the feather is not in free fall. Technically the rock isn't either, but it's close enough. Because
Oh,
they
the
both
feather-
have air resistance.
Oh, makes sense. So should we reword that question in free?
No, because we assume there's no air resistance unless we specifically invoke it. It's just an approximation to make it so we have less confusion.
Okay.
So the reason the feather on Earth will fall slowly is because of air resistance. So that's why on the moon, they fell the same because of no air resistance. Hence this slide here. Okay, y'all ready for woo clap? Question, Vanessa?
Does it have to do with surface area?
It has to do with the cross-sectional area. That is, if the feather is coming like this, it's going to have a lot more air resistance than if it's coming like this. All right, so let us do our woo clap, our first woo clap question. We only have 4 people connected. Go, gadget. Vanessa,
Yes.
now you can use your phone, see?
Right.
Getting there?
Yeah, I'm
You're
here.
there. Okay. Okay, a 5 kilogram iron ball and a 10 kilogram iron ball are dropped from rest for negligible air resistance. Remember I just said, unless it's invoked, we assume the air resistance is not important. The acceleration of the heavier ball will be, oh, sorry. Now you can answer.
Yay.
And look, we already have 2 answers. Dos.
Dos
Tres más.
hermanos.
Thinking is good.
This is your question, so you better talk right.
Okay. Dos más.
I hope you didn't have to be, I don't know.
I definitely.
Uno más.
Don't worry about it. I was just, she pressured me into making an answer and I think it was wrong.
It should be
Don't
right
let-
because I just taught you this.
Don't let Jessica pressure you.
Excuse me. All I am is peer pressure.
Okay. It doesn't look like we're going to get the 5th person to answer, so I'm going to go on at this point. We had 2 people who said the same and 2 people who said more.
So we're equal.
So we have to clear this up because we didn't have clear understanding of this. So I'm going to look at an iron ball. Here's one iron ball. Here's another iron ball. And if we look at the forces acting on these balls, what force is acting on the smaller ball?
Gravity.
So we have force 1 is equal to M1G. What force is acting on the bigger ball?
Gravity.
It's bigger though, right? Because it's a bigger force. So force 2 equals M2G. But then if we use Newton's second law on these balls, we are going to have acceleration 1 is equal to sum of the forces on 1 divided by M1, which is going to be M1G over M1 equals G. And whoops, that was the wrong button. And if I go to number 2, acceleration 2 is equal to sum of the forces on ball 2 over M2 equals M2G over M2 equals G. So they're both going to fall with an acceleration of G. Doesn't matter which one has more mass. Now going back to what Jessica was talking about with the feather. We do have in real life air resistance that's non-negligible. And so if we had air resistance to deal with, even if these two had the same upward air resistances, because this one has a bigger mass, it would have a smaller effect. And so if we included air resistance, then this would have been correct. But without including air resistance, they're the same. So the fact that it said negligible air resistance meant they're going to be the same. Do you understand this?
Yes.
Okay. It's important because after all, I think at this point we all know that Annabelle is asking this question.
Oh, yeah.
So what's going on with parachutists? Parachutists have that parachute out there that is making them have much bigger air resistance. And that air resistance depends on how fast they're falling. If they're falling slowly, the air resistance is small, right? When I go like this, I don't feel any air resistance on my hand. But if you go fast, you can feel the air resistance. And so the faster they go, the bigger the air resistance until they reach what we call terminal velocity. Terminal velocity is the speed an object has when the upward force due to air resistance is equal to its downward force due to gravity.
Right.
And so in this picture, we have a light guy and a heavy guy. The heavy guy has a bigger downward force of gravity, so he's going to have to go faster to reach terminal velocity.
So he's not in free fall.
Neither of them are in free fall, that's correct. Because air resistance is making a
Would
significant
it be
effect.
possible for a parachuter to be in free fall? Is that impossible?
If the parachutist does not pull his ripcord and he's wearing a tight suit with an aerodynamic surface and he faces like a javelin straight down, he could get a lot closer to free fall. Or she.
Or death. Yeah.
Well, yes, that would be the ultimate result if they stayed that way until they hit the ground. Okay. Now we're going to move to another one of Newton's laws, and that is Newton's, well, we've talked about his first law, that was the law of inertia. An object stays in constant motion unless acted on by external force. The second law is what I've been focusing on today, what we learned about in lab yesterday, that the acceleration of an object is proportional to the net force divided by the mass. Well, it's equal to the net force divided by mass. The third law is about interactions between forces. So if we come back to my example with Annabelle punching for her water bottle. If she punches her water bottle,
Yes.
she's going to put a force in that water bottle when she hits it. Agree?
Yes, I will.
Is that water bottle going to put a force in her hand?
Well, yeah, it's a pretty big force.
Yeah, it's just like.
Okay, so we have two answers. One was no, one was yes, it's the weaker. Okay, really simple question. Is she going to feel it when she punches that?
Yes.
Yes. So that means there's a force. There was something pushing on her hand for her to feel it. But then we have a misconception that you all said. You said it's going to be a weaker one. Newton's third law specifies that for every action, there's an equal and opposite reaction. In that statement, action means force. So for every force, there's an equal, not a smaller, and opposite. Opposite means the opposite direction. So when Annabelle punches this, it's hitting her fist back exactly with the same force that her fist is hitting it. So there's equal forces in opposite directions. Now, when Annabelle punches that thing, it goes flying because it has a small mass. If she punched something big, it would have a big mass and it wouldn't move as much. Which do you suppose she can hit harder? That thing or
She
me?
hitting the same. It's just the way the reaction is different.
The speed of her hand could be the same, but the reaction is different, and that's going to change the force.
So that one she's hitting harder.
Actually, this one she's hitting softer because it has less inertia, so it goes flying away. Where she hits me in the ribs, there's a lot more inertia. Good guy. And so her fist has to stop quickly instead of just going pretty much through it. And that's going to result in a much bigger force being applied to me than she applied to that. And likewise, a much bigger force back on her fist. So something that always bugs me when you watch TV shows and they have fights. You know how they love to headbutt?
Yeah.
According to Newton's third law,
I think it's cool.
you hit somebody with your head, the force you put on them is the same as the force they put on you. And so in a lot of these things, they just go forehead to forehead. The forehead is hard, it's like an anvil. So your hard forehead on somebody else's hard forehead, that's going to be a big force on both of you, not just on one. Now, the person who's initiated it can keep his head from snapping back, which is actually a big part of where the damage is done. But in terms of bruising and that kind of thing, potentially breaking something, it's the same for both if you hit forehead on forehead. It's just dumb. Likewise, if you're punching somebody, so I'm going to come to Jessica because she wants it,
Yeah, Jessica.
demo. If I punch Jessica in the forehead,
Come on, Jessica.
what's going to happen?
Come
I mean, avoiding all of the things like, well, she would rightfully sue me for assault.
on, Jessica. That's just too
Her forehead is stronger than my, let's see, metacarpals, than my metacarpals. And so I'm likely to fracture some metacarpals and do minimal damage to her, except for her head might snap back. Right, so that would be dumb. You don't ever want to punch somebody in the forehead. So, and in fact, you don't want to punch anyone. Everyone understands that, right?
No,
But, don't do that.
I'm ready.
Yes, punching somebody in the nose, if you're going to punch them, that's a better place because there's a lot of soft stuff, that cartilage, and even my nose has been broken. That's a lot easier to break. And, the forces, the point here, Newton's third law, the forces are the same on the two objects. So let's look at this picture. She's pushing on the wall. Is the wall pushing back on her? Yes or no?
Yes.
Yes. What do we call the force of the wall pushing back on her?
I'm really trying to think.
The opposite?
Well, it is equal and opposite, but it's not called the opposite force. Although if you're
Does
talking
it
to
have
the law,
like a
it's called the
specific
opposite
name?
force.
The net
Yes.
force.
It's the normal force.
Ah.
So that wall is pushing back on her with the normal force. Is that normal force dependent on her mass?
No,
No, it's not. What is it dependent on?
not for mass.
What is it dependent on? It's simply on how hard she is pushing. It'll push back with whatever is necessary to keep from breaking the surface. And then, which is harder, the force she's putting on the wall or the force the wall puts on her?
The force the wall puts on her. The force she's putting on the wall. Neither.
They must be the same according to Newton's third law. So now let's put this into practical. Let's say that I go golfing, which I've done a few times, but I'm terrible. And I've got my driver here. There's a golf ball down there, and I'm gonna, Happy Gilmore it. I hit that ball. So the head of my club hits the ball. Does the head of the club put a force on the ball when it hits it?
Yes.
Yes. Does the ball put a force on the head of the club when it hits it?
No. Yes.
Yes. And how do the two relate?
They're equal.
They're equal, right. We've advanced from before when you said, oh, but it's much smaller. No, they're equal. So the ball is hitting the club head just as hard as the club head is hitting the ball.
Yeah.
But what does the ball do when you hit it?
Flies.
It flies, it accelerates like crazy, right?
Yeah.
Why does it accelerate like crazy?
The mass is smaller.
Right, because the mass is small. The club head must accelerate too, because it has a force acting on it, but it's a much smaller acceleration because it's much heavier. So let's say that I'm stupid, and I say, well, that works great with the golf ball. Let me try it with the bowling ball. So I come and I Happy Gilmore my bowling ball.
It would go kind of like that?
When the club head hits the bowling ball,
It breaks.
it breaks. Why?
Because the mass.
Because the mass. The bowling ball had much bigger mass or much bigger inertia, and so its acceleration was much smaller. But because that smaller acceleration, the actual force that was applied by that golf club was bigger, so that it broke the golf club. All right, we're out of time. I think my next slide is just a summary slide of the Newton's 3 laws. Oh, nope. It's the statement of Newton's third law. Yeah. Come on, where's the summary? I want to leave on the summary.
1,500 newtons.
There's the summary.
1,500 newtons. Yes.
Good job. Okay, have a great weekend.